Temporary generators and utility power sources generally meet similar voltage and frequency standards. Both aim to provide a stable electrical supply that meets the requirements of most appliances and equipment. However, there are key differences to consider regarding harmonics and transient voltage. Temporary generators can produce higher levels of harmonics and voltage transients compared to utility power. Harmonic distortion caused by nonlinear loads connected to the generator can affect sensitive electronic devices. Voltage transients, such as surges and sags, can occur during startup or load changes. Utility power typically provides cleaner power with lower harmonic distortion and reduced voltage transients. Utility power undergoes extensive conditioning and filtering to meet specific power quality standards. Regarding frequency and voltage regulation, temporary generators may have less precise frequency and voltage regulation than utility power. Frequency and voltage can fluctuate slightly depending on load conditions and generator size. Utility power undergoes strict frequency and voltage regulation to ensure stability. It provides a consistent and reliable electrical supply with minimal variations. Electromagnetic interference, or ME, is another factor. Temporary generators can generate significant EMI, which may interfere with sensitive electronic devices. EMI from utility power is typically minimized due to proper shielding, grounding, and distribution systems. In general, temporary generators can provide comparable power quality to utility power in terms of voltage and frequency stability. However, the generator's size and capacity, the type of load connected, and the condition of the generator and its fuel source may affect the power quality provided by the generator. It is important to consider the specific requirements of the building and the criticality of the equipment being powered. If sensitive electronic devices or equipment with strict power requirements are present, it may be advisable to install additional filtering or surge protection measures to ensure compatibility with the generator's power output. Ultimately, the best way to determine the suitability of a temporary generator's power quality is to consult with the generator manufacturer or an electrician who specializes in power quality testing. Consider these factors: firstly, harmonics; secondly, transient voltage; thirdly, frequency and voltage regulation; and fourthly, electromagnetic interference. Harmonics or distortions in the voltage or current waveform that can cause overheating, equipment malfunction, and reduced efficiency. Transient voltages are short duration, high amplitude voltage spikes that can damage sensitive electronic equipment. Frequency and voltage regulation refers to the ability of the power source to maintain a stable voltage and frequency output, which is essential for the proper operation of many devices. Electromagnetic interference is unwanted electromagnetic energy that can disrupt the operation of electronic devices. To mitigate these potential power quality issues with temporary generators, consider the following steps. Firstly, select a generator with sufficient capacity to handle the connected load. An undersized generator can experience voltage drops and frequency fluctuations, leading to poor power quality. Secondly, use power conditioners or filters to reduce harmonic distortion and voltage transients. These devices can smooth out the voltage waveform and protect sensitive equipment from damage. Thirdly, ensure proper grounding of the generator and connected equipment. Proper grounding helps to minimize EMI and provide a safe path for fault currents. Fourthly, regularly maintain the generator to ensure it is operating at peak performance. This includes checking the fuel level, oil level, and air filter, as well as inspecting the wiring and connections. Fifthly, consider using a generator with automatic voltage regulation, or AVR. An AVR helps to maintain a stable voltage output, even under varying load conditions. Sixthly, monitor the generator's output voltage and frequency to detect any problems early on. This can be done with a multimeter or dedicated power quality analyzer. Seventhly, avoid overloading the generator. Overloading can cause voltage drops, frequency fluctuations, and overheating. Eighthly, use shielded cables and connectors to minimize EMI. Shielded cables and connectors help to contain electromagnetic energy and prevent it from interfering with other devices. Ninthly, separate sensitive electronic equipment from the generator and other sources of EMI. This can be done by placing the equipment in a shielded enclosure or by using a dedicated power circuit. 10thly, consult with a qualified electrician or power quality specialist to assess the specific power quality needs of your application and recommend appropriate solutions. The size and type of generator, the connected load, and the sensitivity of the equipment being powered all play a role in determining the best approach to ensure clean and reliable power. Remember that power quality is not just about voltage and frequency. It also encompasses factors such as harmonic distortion, voltage transients, and electromagnetic interference. Addressing these factors can help to ensure the proper operation and longevity of your electrical equipment. When connecting sensitive electronic devices to a temporary generator, it is crucial to take extra precautions to protect them from potential power quality issues. Sensitive electronic devices, such as computers, servers, and medical equipment, are more susceptible to damage from voltage spikes, harmonic distortion, and other power quality disturbances. Therefore, it is essential to implement additional measures to ensure a clean and stable power supply for these devices. Firstly, use a high-quality surge protector to protect against voltage spikes. A surge protector can absorb excess voltage and prevent it from reaching sensitive electronic devices. Choose a surge protector with a high surge current rating and a fast response time. Secondly, install a line conditioner or voltage regulator to stabilize the voltage. A line conditioner or voltage regulator can smooth out voltage fluctuations and provide a consistent voltage supply to sensitive electronic devices. Thirdly, use an isolation transformer to isolate the sensitive electronic devices from the generator's electrical system. An isolation transformer can block harmonic distortion and other power quality disturbances from reaching the devices. Fourthly, consider using an uninterruptible power supply, or UPS, to provide backup power in case of a power outage. A UPS can also protect against voltage spikes and other power quality disturbances. Fifthly, ensure that the sensitive electronic devices are properly grounded. Proper grounding helps to minimize EMI and provide a safe path for fault currents. Sixthly, use shielded cables and connectors to minimize EMI. Shielded cables and connectors help to contain electromagnetic energy and prevent it from interfering with the sensitive electronic devices. Seventhly, separate the sensitive electronic devices from the generator and other sources of EMI. This can be done by placing the devices in a shielded enclosure or by using a dedicated power circuit. Eighthly, consult with a qualified electrician or power quality specialist to assess the specific power quality needs of your sensitive electronic devices and recommend appropriate solutions. Consider the specific requirements of the devices, the characteristics of the generator's power output, and the potential for power quality disturbances. In addition to these technical measures, it is also important to consider the operational aspects of using a temporary generator. Firstly, ensure that the generator is properly sized for the load. An undersized generator can experience voltage drops and frequency fluctuations which can damage sensitive electronic devices. Secondly, avoid overloading the generator. Overloading can cause voltage drops, frequency fluctuations, and overheating. Thirdly, regularly maintain the generator to ensure it is operating at peak performance. This includes checking the fuel level, oil level, and air filter, as well as inspecting the wiring and connections. Fourthly, monitor the generator's output voltage and frequency to detect any problems early on. This can be done with a multimeter or a dedicated power quality analyzer. Fifthly, keep the generator clean and free of debris. Dust, dirt, and other contaminants can interfere with the generator's operation and reduce its lifespan. Sixthly, protect the generator from the elements. Exposure to rain, snow, and extreme temperatures can damage the generator. Seventhly, follow the manufacturer's instructions for operating and maintaining the generator. The manufacturer's instructions provide important information on how to safely and effectively use the generator. Eighthly, have a backup plan in case the generator fails. A backup plan can help to minimize downtime and prevent damage to sensitive electronic devices. When comparing the power quality of temporary generators and utility power, it is important to consider the specific characteristics of each power source. Utility power is typically generated by large power plants that use a variety of fuel sources, such as coal, natural gas, and nuclear power. The power is then transmitted over long distances through a network of high-voltage transmission lines and substations. Before reaching consumers, the power is stepped down to lower voltages and distributed through a network of distribution lines. Utility power is subject to strict regulations and standards to ensure a consistent and reliable power supply. Temporary generators, on the other hand, are typically smaller and more portable than utility power plants. They are often powered by diesel or gasoline engines and are used to provide temporary power in situations where utility power is not available or is unreliable. Temporary generators are not subject to the same strict regulations and standards as utility power, and the power quality can vary depending on the generator's size, type, and condition. In general, utility power is considered to be cleaner and more stable than temporary generator power. Utility power undergoes extensive conditioning and filtering to remove harmonic distortion, voltage transients, and other power quality disturbances. Utility power also benefits from a large and interconnected grid, which helps to stabilize voltage and frequency. Temporary generator power, on the other hand, can be more susceptible to power quality issues due to the generator's smaller size and simpler design. Temporary generators can also be more prone to voltage drops, frequency fluctuations, and harmonic distortion, especially when subjected to heavy loads. However, it is important to note that not all temporary generators produce poor power quality. Modern temporary generators are often equipped with advanced features such as automatic voltage regulation, electronic governors, and harmonic filters, which can significantly improve their power quality. In addition, the power quality of a temporary generator can be improved by using proper grounding, shielding, and filtering techniques. When deciding whether to use a temporary generator or utility power, it is important to consider the specific power quality requirements of the application. If the application requires a clean and stable power supply, such as for sensitive electronic devices, then utility power is generally the preferred option. However, if the application is less sensitive to power quality issues, such as for powering construction equipment or lighting, then a temporary generator may be a more cost-effective solution. Ultimately, the best way to determine the suitability of a temporary generator's power quality is to consult with a qualified electrician or power quality specialist. A power quality specialist can assess the specific power quality needs of the application and recommend appropriate solutions to ensure a clean and reliable power supply. One crucial aspect to consider is the transfer switch mechanism. A transfer switch is used to switch the building's electrical load between the utility power and the temporary generator. There are two main types of transfer switches: automatic and manual. An automatic transfer switch, or ATS, automatically switches the load to the generator when utility power is lost. Once utility power is restored, the ATS automatically switches the load back to the utility. This type of switch is ideal for critical applications where power outages can cause significant disruption or damage. A manual transfer switch, or NTS, requires manual operation to switch the load between the utility power and the generator. This type of switch is less expensive than an ATS but requires someone to be present to operate it during a power outage. When selecting a transfer switch, it is important to consider the following factors. Firstly, the switch's current rating. The switch must be able to handle the maximum current that will be flowing through it. Secondly, the switch's voltage rating. The switch must be able to handle the voltage of the electrical system. Thirdly, the switch's type. Choose the type of switch that is appropriate for the application. Fourthly, the switch's features. Some switches have features such as automatic transfer, voltage monitoring, and surge protection. Fifthly, the switch's cost. Compare the cost of different switches before making a decision. In addition to the transfer switch, it is also important to consider the grounding and bonding of the temporary generator system. Proper grounding and bonding are essential for safety and for minimizing EMI. The generator should be grounded to a grounding electrode system that meets the requirements of the National Electrical Code, or NEC. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods or ground plates, that are connected to the generator's grounding terminal. The generator should also be bonded to the building's electrical system. Bonding is the process of connecting all metal parts of the electrical system together to create a low impedance path for fault currents. This helps to protect people from electric shock and to minimize EMI. The bonding should be done using copper conductors of the appropriate size.